When it comes to AI, we've all kind of bought into this one big idea, right? Bigger is always better. More data, more power, more parameters. That's been the surefire path to smarter AI. But what if that core belief is just plain wrong?
All right, take a look at this number. That's 1.7 trillion. This is the number of parameters in a huge state-of-the-art model. We're talking 1.7 trillion little dials that the AI gets to tune. I mean, it's a number so big you can't even really picture it. This is what we mean when we say big AI.
Okay, now look at this number. 7 million. Not billion, not trillion, million. This is how many parameters are in a brand new model that's turning heads called the Tiny Recursive Model, or TRM. And yeah, you heard that right. It's not a mistake. We're going from the land of trillions all the way down to a few million. So this sets up the absolute killer question we're going to tackle. How on earth can a model that's, and I'm not kidding here, 240,000 times smaller, not just hold its own, but completely dominate the biggest models out there on specific, really hard problems?
So here's how we're going to break this down. First, we'll tackle that bigger is better myth. Then, we'll see where these giant AIs totally fail. We'll look at a complex early attempt to solve it, and then the tiny model that changed everything. After that, we'll see the mind-blowing results and talk about what it all means for the future of AI.
All right, let's dive in. First up, the bigger is better myth, and this whole race to trillions of parameters. So for years, the path to making AI smarter seemed really, really simple, right? Just add more data and more parameters. This whole idea, they call it scaling laws, is what gave us the amazing large language models we have now. The ones that can write code or a poem on demand. But, and this is a big but, chasing scale above all else created a huge blind spot. And that's where our story really began. So this big blind spot, what is it? Well, it turns out when you throw certain types of really hard puzzles at these giant AI brains, they just completely choke. And we're talking about puzzles that are, conceptually simple for us humans, but turn out to be a nightmare for AI. Like, think of those expert-level Sudoku puzzles that make your head spin, or trying to find the one correct path through a super tricky maze. But the real killer? It's these things called ARC-AGI puzzles. ARC stands for Abstraction and Reasoning Corpus, and they're all about looking at some weird geometric patterns and figuring out the logic to continue them. It's a pure reasoning test. And when I say they choke, I mean it. Just look at these numbers. You've got massive models like DeepSeek and Claude with hundreds of billions of parameters scoring a big, fat 0 on extreme Sudoku. 0. Even a powerhouse like Gemini Pro barely cracks 5% on those ARCs puzzles. The takeaway here is crystal clear. Just making these models bigger is not helping them solve these kinds of reasoning problems. Okay, so this epic failure obviously got researchers thinking we need a totally new plan. The first real breakthrough came from something called the Hierarchical Reasoning Model, or HRM. And it was a cool idea, but man, was it complicated. But before we dig into HRM, we have to get our heads around the central concept, which is recursive reasoning. The best way to think about it is like a sculptor. They don't just hit a block of marble once and poof, a statue appears. Nope. They use their chisel, make a cut, step back, look at it, and then use that exact same chisel to make the next refinement. And they do that over and over and over again. It's that process of gradual improvement that we're talking about. So HRM tried to do this, but its process was a bit of a mess. I mean, it was juggling two different neural networks, a low-level one and a high-level one, and they were working at different paces. It had to rely on this super complex mathematical theorem just to guess at how to learn properly, and it even needed a whole extra step just to decide when it was done thinking. It was, a lot to handle. But here's the crazy part. It actually worked. Well, kind of. It went from 0% accuracy on those insane Sudoku puzzles all the way up to 55%. That was a huge deal. It proved the whole recursive idea was solid. The problem was the model itself was clunky and complicated, and it really left everyone wondering, okay, this is cool, but couldn't we do this in a much simpler, better way?
And the answer to that question was a huge, emphatic yes. This is where our hero, the Tiny Recursive Model, TRM, steps onto the scene. It basically took that core gem of an idea, recursion, and just threw all the complicated junk in the garbage.
Just look at this side by side. It's awesome. HRM had two networks, 27 million parameters. TRM, just one tiny network, 7 million parameters. HRM needed that complicated math theorem. TRM doesn't need it at all. It just learns. HRM needed 2 passes to train. TRM does it in 1. It's just a beautiful example of simplification.
And its process? It's just so elegant. Step 1, think about the problem with the one tiny network. Step 2, use that same network to make your answer a little better. Step 3, repeat. That's it. No weird levels, no crazy math, just a simple, powerful loop. And the smart ideas here are all about simplicity. Instead of guessing, TRM learns from the entire thinking process. It has a way simpler way of knowing when it's done. But my favorite part is this. The researchers tried a 4-layer network, and it did worse than a simple 2-layer one, because the smaller network was less likely to just memorize the answers. I mean, it's the perfect example of less is more.
Okay, so we've got a model that's smaller, way simpler, and just more elegant. But the million-dollar question is, does it actually work any better? Well, the proof is in the performance. Let's look at the numbers.
And wow, these numbers are just nuts. Remember Sudoku Extreme? The big models got 0. HRM got to 55%. TRM, 87.4% accuracy. Just incredible. Then you look at the hard mazes, and a version of TRM jumps from about 75% with HRM to over 85%. I mean, it's not just a little better, it's a huge leap forward everywhere.
This bar chart says it all, really. Just look at that jump from HRM to TRM. That's not a small step up. That is a game-changing breakthrough. And again, they did it by making the model smaller, not bigger. It's wild.
And hey, this wasn't just a fluke on Sudoku. TRM also went on to set new records on those super hard ARC-AGI geometric puzzles, beating the older HRM and almost all of the giant language models.
Okay, let's zoom out. What's the big takeaway here? What does the insane success of this tiny little model tell us about where AI is heading?
I think there are a few huge takeaways. First, smart architecture can absolutely crush brute force scale. It's not just about how many parameters you have, it's about how you use them. Second, it proves that these tiny, specialized models can be way better than the giant do-everything models for specific hard tasks. And finally, this whole recursive reasoning idea, it's a seriously powerful tool for solving complex problems.
And all of this leaves us with one last really exciting thought. For so long, bigger is better was treated like a law of physics in AI. This research just proved that law can be broken. So it makes you wonder, right? What other fundamental rules of AI are we all following that are just waiting for the next big, simple idea to come along and shatter them to pieces?